Hello everybody, I'm András Németh, the CTO of LynxAnalytics, and I'm going to show you how simply you can do some email graph analytics with LynxKite, our graph analytics platform. So basically I'm just starting with creating a new workspace, which is basically a representation for some graph analytics workflow. Let's call it Lynx email graph, because we are going to actually look at the email graph of LynxAnalytics, of course in an anonymized version. And I have the starting data as a CSV file. I will show you in a second what is in this. It's as simple as grabbing the file, pulling it to the workspace, and waiting a little bit. You can see that some computation was in progress here, and I can actually look at the output. And basically, it's a very simple data. I got it just from Gmail email log search and some pre-processing and anonymization. Basically, you have a date for each message. You have a sender, an ID for a message, and the receiver. So the same message ID actually appears multiple times. Like if it's a message sent for multiple people, then you would see the same message ID multiple times with different receivers. So this is our data, and to make graph out of it, we are just going to look at the graph construction operations. And there is one which is basically takes a table and creates a graph out of this straight away. The parameters, I have to say, I have to tell the system what is the column which designates the source vertex of an edge, and another column which is going to be the destination. So I'm just going to go ahead and choose from here to here, and let's see what happens. So now the system is converting this table into a graph, and in the meanwhile, let me try to explain what you can see on this view. Basically, this is the metadata about the graph being created. We don't yet know, or actually now we do, that this graph has 79 vertices and 123,000 edges. Basically, every single message is a new edge in this case. That's why we have so many edges relative to the number of vertices, which is really basically the size of our organization. Down here, you see that every vertex has certain attributes. In this case, we just have an ID and the string ID. Basically, the ID is just an internal identifier. You don't need to care too much about it. And string ID is the identifier taken from the data. So for example, if I look at a histogram of the string ID, then I will see that basically those are, fake first names. In the real data, you would see like the actual names of the people or email addresses. And on each edge, I have all the fields which corresponds to the original columns of the data. So here we had date, from, mid, and to. And basically every row of this table became an edge in the graph, and we retained all these attributes. Most of those attributes, actually any of those attributes, we don't not going to care too much about, and we are going to lose them in just a second. So again, if you look at this graph, we see that it's way too many edges. Like I don't really want a single edge for every message. I just want one edge between any two people, and maybe have the number of messages between those two parties as an attribute. Luckily, we have an operation just for that. So we have the structure operations here, and there is this merge parallel edges. It's exactly what we need. Basically, if there are two vertices and there are multiple edges going from one to the other, then this is going to take all those edges and create a single edge from this. It actually works without any parameterization, but what I can do in extra is I can configure this to take some aggregation of the original edge attributes to the new aggregated edge attribute. So the only thing I'm going to care about is that between those parties, how many different messages has been sent. So I'm going to look at this mid, which is the message ID, and I'm going to select the count distinct aggregation. As a result, let's see, we get a new graph. The system already knows that the number of vertices didn't change, so it knows that without any computation. Now we have also the number of edges. We can see that from it went down by 121,000. So actually now we are down to 2,000 edges, which is a much more reasonable number. And you see that also the list of edge attributes has changed. we lost all the original attributes because I didn't choose aggregation for most of those, except for the mid, for which I have a mid count distinct attribute. So actually, that's pretty much it. We already have a graph. We can even take just a very quick peek at it. Like what happens in this visualization is that the system selects a random vertex and shows us the neighbors of it. It's just a small segment of the graph. I can put some attributes on it. Like we see that there are all these people here, and if I hover on them, I can see, for example, what are the neighbors of Francisco. I can just hover and see Michael's neighbors, and so on and so on. So okay, we basically have our graph. It was as simple as that. And as the next step, we want to kind of see a little bit of an importance of our people based on this graph. Like we are just going to use the first very standard thing which comes to mind, which is PageRank. We have a PageRank operation. Or you might notice that I did something very fast. Basically, if you click on this magnifier glass, you can start typing the name of the operation. I don't even need to know which category this is. So I just started PageRank, and then I could select the operation right from here. Again, as usual, if I click on the box, I can configure this PageRank. I don't need too much configuration. The defaults are fine for now. Let's do a little bit more iteration. Let's say we do, 20 iterations in the computation of PageRank. And let's look at the result. So maybe let's put this in a table. And all I basically want to see every attribute from the vertices, which are the people in our case. I don't need this limit, but I actually want to order by PageRank because I'm mostly interested in the important people according to this graph. So let's see the results. After a little bit of computations, hopefully we are getting to a list. Yeah, so you see now from our graph, we again went back to a table using this SQL statement. And basically every line here is a person. We see their PageRank, and well, this ID is not very useful. I could get rid of that if I change the SQL to not include, but this was the simplest. Now, because of the anonymization, you have no clue whether these people are indeed important or not. But I actually, in my mind, know the actual mapping. And I know that Sam being the very first is extremely weird. But Sam is actually not working for LynxKite anymore. He used to work with us, and now he's doing something completely different, but he's still in touch with us. Sometimes he refers as clients and so on, but he certainly shouldn't be the most important guy in the organization. What is going on here? So let's try to take a look. Like we are going to remember that we actually want to take a look at Sam. Let's look at Sam in our graph. Basically, I'm going to do this visualization again, but I'm going to select specifically the guy we are interested in. So I want to see the guy whose string ID is nothing else but Sam. And I'm going to pick him as the center of the visualization. Let me put on the labels. And where are you, Sam? Sam is here. So what we can see is kind of interesting. Like he has a lot of incoming edges. It's most probably because he was included in some email chains, but it's still fairly sparse. He doesn't even have a lot of neighbors. And actually I can do one more thing to make it even more visual. I can add this mid count, like how many messages we are talking about, as the width of the edges. Let's see how it looks now. Yeah. So actually we see that not only that SEM is connected to very few people, actually the strength of the connections are much weaker than a typical one in the graph. So what happened here? Did we just miscalculate PageRank? No, basically the solution is that SEM is really acting as a PageRank trap here. Like if we look closer, we see that the guy actually has a loop edge and he has no outgoing edges at all. Like this is really a perfect trap for the PageRank. Like basically all the probability goes into that because actually the guy is connected to important people like Gabriel actually represents our chief data scientist. Graham is actually our CEO. Aman is the head of our operations. So he's connected to all these people. He's getting PageRank from all these people, but he never gets rid of it because of this loop edge. So this is basically an error. We really have to tweak a little bit of this graph to make it better. Actually, we made two big mistakes. One is that we have a lot of loop edges. Actually, loop edges doesn't make any sense from a PageRank point of view. Like we straight away want to get rid of loop edges. And the other mistake we made is that we actually didn't care about the width, in this case, the number of messages when we computed PageRank. So in LynxKite, if you recognize such a mistake, it's extremely easy to go back in your workflow and just add some corrections. Like what I'm going to add is I'm first going to get rid of loop edges. There is an operation for that. I'm going to do that before the PageRank. So I'm going to connect the output of match parallel edges here and connect back to PageRank like that. And the other mistake I mentioned is that we should actually use in the PageRank computation this attribute, this mid count distinct to actually take into account how important an edge is, like how many messages are going between those two people. So if I do these changes, I can just click again on the result. And because the flow is now different, the system has to recompute everything. And yeah, this is happening. Like what you see in this bottom right corner is actually Spark stages. Like the whole system is under the hood using Spark, so it can be distributed and that it can work in very large data sets as well. Okay, so actually now the results start to make a lot of sense. Like you might remember I mentioned that Aman is the head of our operations. Of course, he's connected to a lot of people and he's very important in the communication network. Graham is our CEO. Gabriel is our head of data science. So really now the PageRank starts to make a lot of sense. Okay, so next step, what I'm trying to do is to find some groups in our organization, like basically try to find some clusters which are people who work very closely together. So we have a lot of clustering operations, but the one I'm going to use is the modular clustering. I'm just take this find modular clustering box. And let's scroll it down a little bit. Let's make it a little bit different section of my workspace. And like this final graph, I'm connecting this in. Actually, I don't think I even need to change much attribute the parameters. Let's see what's the result. So now there is a new thing here, segmentations, which is like groupings of the vertices. And we have a single one, which was created by this operation, the modular clusters. So let me open it. Let's see how it looks. Again, we are now just looking at the metadata. So we can already see that there will be 5 clusters created. They actually cover the whole vertex set. This is always the case by definition for modular clustering. And there is actually also a so-called scalar computed here, which is like a single number, which is representative for the whole clustering. It's basically like how good this clustering is from a modularity point of view. So this is not a great value. Like actually, if I just put everybody in a single cluster, then the modularity would be by definition 0, and we are just a little bit above that. I mean, it's like the maximum possible value would be 1. So it's like not absolutely terrible, but still this shows that, okay, we managed to find only 5 clusters and a very low modularity. And actually, I can also visualize these clusters and try to judge if this makes sense. So I'm going to create a graph visualization. And let me configure it. So I actually want to see all vertices. I want to actually not only see the base graph, but I also want to see it together with the clustering. Let me visualize those as well. I also want to see all the clusters, and I'm going to put on some attributes on the visualization. So I'm going to have the size of the cluster as the label and the size. I'm going to put on the names of the people as label. And yeah, maybe let me add also this mid count, this thing like the importance of the edge as an edge width. So okay, now I configured a fairly complex visualization. Let me open it and let's have the system do the computations. It's now also like we are sending over quite a lot of data. You will see it's going to be a very busy graph. And we are actually going to filter a little bit on the foreground to be able to see something meaningful. Yeah, okay. So here we are. On the left-hand side, we actually see the original graph. It's extremely noisy, lots of vertices, not much you can see about it. The right side is much easier to see. Like we have the 5 clusters that was created. We see the size of each. And actually each of these is connected to the set of people that belongs to this cluster. In this form, it's still like you can see somewhat what's going on, but you can actually make the visualization much less busy if I ask the system to filter the left side to only the members of this cluster. If I do that, then I'm actually seeing that those are the members of this cluster, and I can take a look the same way to the other clusters. And okay, again, for you, it doesn't really mean anything. Like the reason I'm showing it is just to show off how you can look and debug what's happening in such a case in LynxKite. But actually on the real data, I can see that these clusters are not very helpful. Like they are sometimes very mixed up, and it's not really corresponding to any actual meaning, which is again not surprising after we see the low modularity level. Basically, the system was not able to find very meaningful cluster. So what could be the problem here? So the reason modular clustering fails on this graph is because of the structure. Like this is a typical organization graph with a very kind of hierarchical structure. There are a few vertices who corresponds to our leadership team, who is connected to all over the graph. So it's really like they connect all different parts and groups, and they are really in touch with everybody. And it makes it really hard for a clustering algorithm to cut the graph, because wherever we cut the graph, we are going to cut through those leadership edges, and those people are actually very communicative. So it's really like a big chunk of edges that any good clustering would cut through. So how we can solve this? Basically, what we are going to do is we are going to deprioritize edges which go to those very, very active people. Like we are going to change the weights of the edges in a way that if they are connecting to a very active person, then we are going to demote the importance of the edge. So we compute a derived weight this way and redo the modular clustering. So let me do this. The first step I'm going to do is to compute this kind of how active somebody is. It's basically a degree-like metric, but I'm going to want to use the amount of emails, not just the number of people they are connected with. So I'm going to do an aggregation. I'm going to need this aggregate edge attribute to vertices. Let me connect this to the same point where we started the modular clustering before. Let me configure this. So this operation takes some edge attributes and aggregates them to some way to the vertices that those edges are connected to. In our case, we are actually going to do this on all edges, not just incoming or outgoing, but both incoming and outgoing. And we are going to take this mid count discount distinct and basically just take the sum of it. Yes. Now we end up with a new vertex attribute, the very nicely named edge mid count distinct sum. So of course this is an ugly automatic name because we basically took the sum of the mid count distinct from the edges. Let me actually rename this just to make it easier to work with. Oh, it's not an edge attribute, sorry, I need to rename a vertex attribute. And I'm just going to call this thing degree because it's basically a weighted degree. Once we have this, we are going to use this to define our new edge weight. To define a new attribute on the edge, I can use this derive edge attribute operation. And this is actually a very powerful thing. Like what really makes a huge power in LynxKite is all these aggregation and derivation operations, which are really extremely flexible and powerful. You can basically use any kind of Scala code here, and you can refer to the existing edge attributes and also the attributes of the source and destination vertices. So let's call this weight, and let's actually use this formula. Basically what I'm doing, I do this existing mid count distinct, basically how many messages are going between those parties. And I'm going to normalize it. It's a very standard graph normalization technique. Basically, I take the source degree, the destination degree, those are the ones that we just computed, multiply them out. So now we define this new edge attribute. You can see it here. You can take a look at this histogram. It's a pretty nice long tail distribution. And now let's do the modular clustering based on these weights. All I have to do is to redo this modular clustering operation. But now I'm going to set this weight as the edge weight that's used by the algorithm. If I look at this modular clustering, I'm actually getting much better results. So now the modularity is, instead of 0.14, we have a modularity of 0.36, which is a much higher value. It shows that indeed using this weight, the graph behaves much more like a modular graph, something that can be efficiently clustered. And I can also just basically connect the very same visualization now to this new modular clustering. All I have to do is to change the input of this existing visualization box. And now we see the new clusters. This part is not so visually clear because of the anonymization, but I checked this on real data, and if I look at these clusters, they actually make sense. Like now we see clusters which corresponds to things like our HR function, another one which is our finance and admin function, another one which is a big group of project-related people like data scientists and data engineering. We have another group which is the corresponds to our Hungarian office, which is also our engineering hub. So those people are also working together a lot. So with these tweaks, actually, we managed to understand this graph pretty well, to really find the meaningful clusters in the organization. This is basically it that I wanted to show you today. Really, the point is not this exact analysis, because of course this is simple and this is something we did in like 20 minutes, but to show you the workflow and how you can work with LynxKite on such a problem, like how you can iteratively look at the results, tweak your workflow very quickly, see the changes that those modifications to the workflow created on the results, and just keep going. I hope you like this, and thanks a lot for your attention.